We'll start to share the screen here. All right, well, thank you both very much for coming today. What I want to do for the next couple of lessons is go over this idea of quasi-affine varieties and then quasi-projective varieties. So if you really think about it, so far we've talked about varieties, we've talked about what does it mean to be singular, non-singular, but we haven't really talked about projective varieties in any real sense. So, we've only talked about it kind of when we did things at the start of the course, when we kind of talked about projective space, but then eventually I want to build up to a really fancy way of doing projective varieties. And what we're going to do today kind of is going to hint at how we're going to do that. So today we're going to talk about quasi-affine varieties, and then Friday I want to get into quasi-projective varieties. And once we do that, then basically we'll have defined one of the most general things that you can define in algebraic geometry. So today, we're going to spend probably about just under half of the lecture reviewing things, because there are some concepts that I want to make sure you feel comfortable with, and then we'll jump into all the new stuff about the quasi-affine varieties. So first, just a few quick announcements. Monday's lecture is now online on YouTube, so hopefully you'll be able to view everything there. I'll have office hours at the usual time, usual place, so 11 a.m. after class and then 4 p.m. in the afternoon. And as a reminder, the next homework assignment is due this coming Friday by 5 p.m. That's homework assignment number 8. A lot of what's in homework assignment number 8 is just supposed to build on some of the definitions that I gave Monday, and then we're going to review these same definitions today. So if you wanted to see some of the details of the definitions, then I definitely recommend attempting to do the homework assignment. So, our recap. In everything that we do today, let's define 3 things. Number 1, F will be an algebraically closed field. Unfortunately, a lot of what we're going to do here doesn't make any sense if it's not algebraically closed. Some of it is, but just to simplify a lot of the ideas, we'll assume that our F is algebraically closed. So think of F as like the complex numbers. We'll denote R as a polynomial ring in n variables, and we'll denote O as an integral domain. So think maybe like the integers. So first we have this idea of the height of a prime ideal. So given a prime ideal I of our integral domain O, the height here will be the length of the longest chain here we can write down. So here I0 is the 0 ideal, IM is the prime ideal I, and then we'll just have some chain of ideals that are not equal to each other as we go from bottom to top. So the length of the longest chain, this length M, is what we're calling the height of our ideal. So for example, if we were dealing here with this maximal ideal of R that is generated by these n polynomials, x1 minus a1, x2 minus a2, through xn minus an, this has height n. So very roughly speaking, you want to think of height as like the number of generators of the ideal. Right? That's kind of rigorously what this is. It'll tell you the number of generators. Next, we have this concept of a ring being Noetherian. Simply put, a ring is Noetherian if, whenever you have a chain of ideals, then this chain has to stop increasing at some point. It has to terminate. So some people call this the ascending chain condition, ACC. So again, this says that if I have an ascending chain of ideals, then at some point, I just can't keep getting larger and larger. At some point, it has to look like things are equal to each other. Right? So for example, if we're dealing with a ring in the following form, we'll take our ring R and we'll quotient by an ideal I, then this here is always a Noetherian ring. So you can think of Noetherian in a couple of different ways. One, it's a quotient ring that you get coming from the polynomial ring R. And 2, it's a condition that you write down that guarantees that the height of a prime exists. Right, so again, you know that the height of a prime will exist when you know that this chain here can't just arbitrarily get large. So that is, this integer m here does have a bound. Right. Then third, we put both of these together to talk about the cruel dimension. So remember that the cruel dimension is the largest height that you'll have as you range over all prime ideals I. Right, so again, the cruel dimension, what we're calling dim of O, this here will be the largest integer for the height that you can find as you range over all prime ideals. So for example, if we're dealing with the polynomial ring in n variables, then this here has dimension n. So again, you want to think of dimension roughly as like the number of generators. So in this case, the dimension is n. And just put this out there because we'll use this a little bit later. There are three different ways, equivalent ways you can think of dimension 1. So dimension 1 is the same thing as saying every non-zero prime ideal has height 1. Remember that it has height 0 if and only if it's the zero ideal. So if every non-zero prime ideal has height 1, we'll say that our ring has dimension 1. And that's equivalent to saying that every prime ideal is one of two types. Either the prime ideal is the zero ideal, or the prime ideal is a maximal ideal. Right, so again, that's what it means for a ring to be dimension 1. That every prime ideal comes in one of two types. Either it's 0 or it's maximal. Okay, so these are three constants that we had here leading up to the dimension of a ring. So any questions on these three here? Okay, all right, let's keep moving on. Next, we talked about what it meant to be integrally closed. So we set it up as follows. Again, say that O is an integral domain, so it has no zero divisors. Then we can talk about the smallest field containing O. So this is what we call the quotient field of O. Right, so again, it's the smallest field that contains it. The integral closure is this weird set here, O prime. So it says, take those elements in the quotient field and look at those that have to be the roots of some polynomial with the coefficients lying in our ring O. Right, so again, there should be elements in the field K where these elements are roots of some polynomial where the coefficients lie in the integral domain O. Right, so we'll do some examples of this later today. So this O prime is an integral domain. It contains O, and we'll say that O is integrally closed if O equals O prime. Right, so again, O prime is always greater than O, so we'll say it's integrally closed if we have equality, if O prime equals O. So as an example, the polynomial ring in n variables is a ring that is integrally closed. Right, so one of the tricks that we'll have to do is figure out when a ring is integrally closed. Okay. So once we have this, then now we can piece together what does it mean to be a non-singular variety. So again, remember that O here is an integral domain, and we're going to say that spec of O is an abstract variety. Right, so again, spec of an integral domain is what we're calling an abstract variety. So remember, literally the points of O of X are prime ideals. Right, so the points of X are just the prime ideals of O. And so we'll think of O here as the coordinate ring of X. Okay. So here you want to think of this as someone is giving you O, an integral domain, and now you're writing down a variety. That's what we mean by spec of O. If this integral domain has two other properties, that is, it's Noetherian and integrally closed, right, so two other properties, then we say that our spec is a non-singular abstract variety. Right, so again, non-singular means that it's an integral domain that's Noetherian, integrally closed. So if we have all of those three, integral domain, Noetherian, integrally closed, then we can define the dimension of our variety. So I want to point out that dimension only makes sense for a Noetherian ring because you need to make sure that the heights of primes are bounded. Right? That's the idea of being Noetherian, that the heights are going to be bounded. So this dimension here makes sense. Integrally closed means that we have this condition here about the dimension of m mod m squared for all maximal ideals m. Right, so again, we'll come back and say a little bit more about this today. So as an example, let's go back to our polynomial ring R. Well, we know that that is an integral domain that is both Noetherian and integrally closed. So we think of spec of that ring as our affine in space. So again, spec of R should be affine in space. There actually is a typo here. This shouldn't be O, this should actually be R. So this is what we're calling affine in space. So of course, this here is a non-singular abstract variety, and it has dimension n, because we want the dimension of the ring R. So now you can see everything seems to match up perfectly, because we have a ring R. We know that its dimension is n because it's generated by n variables. We have our affine in space. This consists of n-dimensional vectors, so its dimension is n. So all of the dimensions match up exactly in the way that you want them to. Yeah, question?
So how is this definition of the affine in space related to our previous, more intuitive definition of it?
So that's what I was going to go over in the next slide. To kind of remind you how that works. So yeah, but thanks for that. But I definitely will go over that in just a moment on the next slide.
Cool.
Okay. All right.
Can I ask something else real quick?
Yeah, sure.
So in the paragraph right before the last one, is I guess like, is the choice of M irrelevant?
That's right. This should be for all M, for every maximal ideal.
Okay, so it's not the maximum, but if you choose any of them, it's going to be the same.
That's right. If you choose any of them, then it's going to be the same. Right. In fact, this is actually part of the definition, is that for it to be non-singular, this dimension is the dimension of O for all M. So it's kind of built in. So I'll just kind of explain this on the next slide. But the point is that this dimension M mod M squared should be the same for all M, and that's equivalent to being a non-singular variety.
Okay, thank you.
Okay. All right, any other questions here? All right, okay, let me just say a couple other things here. Now, this is the general definition of an abstract variety. So let's focus on the case when we have an integral domain of dimension 1. Right, remember, so I talked a little bit earlier about what were the cases of being dimension 1. It just means that every non-zero prime ideal is maximal. So in that case, we will say here that spec of O is an abstract curve. Right, so more generally, I should say more specifically, if O is an integral domain, which is Noetherian, integrally closed, and has dimension 1, so now 4 things, we'll call O a Dedekind domain. So in that case, then spec O is now a non-singular curve. Right, so now we've kind of put everything together. So you'll see here that in general, if we have an integral domain, we have a variety. An integral domain that's Noetherian and integrally closed, we call that a non-singular variety. And an integral domain, Noetherian, integrally closed, dimension 1, that gives us a non-singular curve. Right, so now we're kind of putting on a lot of adjectives to kind of go back to what we're used to. Right. So let me go back to this question that was asked earlier. How does this match up with everything that we've done up to this point? So let's kind of come back and make sure that we have this very down-to-earth definition. Let's consider our polynomial ring R in n variables. And let's pick now m polynomials f1 through fm. Right, so pick any m polynomials that you want. Consider this ideal I. And let's assume now that this is a prime ideal, so that this quotient ring here is an integral domain. Right, so now we're starting with m polynomials and n variables. Right, so start with m polynomials and n variables. I can assume that it's a prime ideal. So then we have now this ring O, this quotient ring. And now I can consider this set X. So this is the set of points where these polynomials vanish together. right? So this is like everything that we've been studying here throughout the course. So this would be things like conic sections and Pell's equations and all of these. So again, just collection of polynomials, and I'm trying to set everything equal to 0. So once we have this, we call this, of course, a non-empty Zariski closed subset. So we just have this fancy words here. And let's let MP be the maximal ideal according to a point in X. So here, this is the ideal generated by the polynomials xk minus ak. Right, so again, just take these difference, xk minus ak. There will be n of those. So I can generate the ideal, that is the maximal ideal. I can take a look at the square of that maximal ideal. So now what we're doing is we're looking at the ideal generated by the following products: xi minus ai times xj minus aj. So there are n choose 2, actually they're a little bit larger than that, n choose 2 plus n squared, number of such polynomials. Right, so again, all that we're saying here, sorry, I said plus n squares, plus n choose 2 plus n. So that's the number of squares that we have sitting in this here. Right, I'll try to give an example of this in just a moment as well. So this is what we mean by the maximal ideal MP, and this is what we mean by the square of the maximal ideal, MP squared. So then the quotient, m mod m squared, is what we call the cotangent space at P. And this here turns out is a vector space. And we had the statement before that it's non-singular at P, right? Our non-empty Zariski closed subset is non-empty at P if and only if the dimension is this here, n minus m. But notice that this happens at each and every point P. So when n equals m plus 1, that is that the number of variables is 1 more than the number of equations, then we can say the following. We have a non-singular curve if and only if this cotangent space is one-dimensional for all maximal ideals. So notice that that means I have to compute this dimension for every maximal ideal I can write down. It's not just enough to say that it's true for one, I have to say that it's true everywhere. But that's what it means to be non-singular at a point. That remember that point, P, I can associate to this maximal ideal, MP. So now I have to take a look at every maximal ideal, M sub P. And take a look at this MP mod MP squared. Right? Make sure that that is a one-dimensional vector space. So this is all equivalent to saying that this ring O is a Dedekind domain. So there are 3 different ways in which you can think of things here, and it just depends upon what you feel more comfortable with. So again, if you go back to, let's just start with m polynomials and n variables, then we can talk about the Jacobian, we could talk about derivatives. There's a way we can translate the tangent space into the cotangent space, and now it's just a matter of looking at these m mod m squareds. If you don't like that, then you could just say, take a look at the quotient R mod I, which is what we're calling our coordinate ring O, and ask, is that a Dedekind domain? And if the answer is yes, then we know that we have a non-singular curve. Right, so either one of these will be perfectly fine. Right? So let me give maybe a more down-to-earth example of this that goes over what we did in the last lesson. So let's go back to a cubic curve that looks like an elliptic curve. Y squared is equal to x cubed plus ax plus b. And let's take a look now at this coordinate ring, which should be the polynomial ring mod the ideal generated by this cubic, y squared minus x cubed minus ax minus b. So remember that we can actually think of spec of the coordinate ring as the points on the elliptic curve by doing 2 things. Every affine point, P, corresponds to this maximal ideal, MP here. Right, so notice I have x minus xp and y minus yp, so they're the generators. And I can think of the point at infinity, because I just have one more, as corresponding to the zero ideal. Right, so again, affine points correspond to the maximal ideals. The point at infinity will correspond to our zero ideal. So we're going to think of EF as spec of the coordinate ring. So we know that E is non-singular if and only if the discriminant is non-zero. And we just said earlier that this is also true if and only if the coordinate ring is integrally closed. So it turns out that the coordinate ring is always an integral domain that is Noetherian. Right? Doesn't matter at all what the E is. OE is always an integral domain that's Noetherian. The non-singularity of E comes down to whether OE is integrally closed. Right? That's what we have to check to make sure that we have a Dedekind domain. So we worked this out before. If the discriminant is zero, then we actually do have a singular point. So we know that our curve is singular. And actually, you can go one further. Take a look at this element T here. So this is integral over OE, right? Meaning that it's the root of a degree 2 polynomial with the coefficients in OE. However, it is not an element of OE. So that means that this T is an element of OE prime, but it's not in OE. So T is in the integral closure, but it is not in OE itself. So this is an explicit element that actually tells you that the coordinate ring OE is not integrally closed. Right, so again, if the discriminant is equal to 0, then we actually have an element here that is not in the original ring that is integral. So our OE is not integrally closed. Okay, any questions up to this point here? Okay, all right. So now for the last half of class, I do want to start to go over some examples of Dedekind domains and then eventually get into what do I mean by quasi-affine varieties. So let's maybe just start with some examples of Dedekind domains. So remember the philosophy is this. Spec O is non-singular if and only if O is a Dedekind domain. Right, so now this is just purely a question about rings. Right, so you give me an integral domain and we're going to try to ask some questions. So the first example here is actually pretty nice because the integers is a Dedekind domain. So spec Z is a non-singular curve. Now remember, this is supposed to look really weird because you want to ask, are there any defining equations? And in this case, there are no defining equations. You can ask, well, what's the tangent space? Remember that the tangent space, you really want to correspond to the cotangent space, this MP mod MP squared. So you have to take a look at the maximal ideal. So remember that a maximal ideal corresponds to a prime. So now we're looking at something like P mod P squared. Right? That's just kind of roughly the idea. Right, so in this case, we actually do have a nice non-singular curve. So let's try to do a slightly more complicated example. Fix a square-free integer d, which is not a square, and let's consider this ring here. So z adjoins square root of d. Now you may recall we actually looked at this towards the very start of the course when we were looking at Pell's equations. Right, so here x and y are integers, and we're looking at numbers of the form x plus y square root of d. So you can actually work out that this is a Dedekind domain if and only if d is congruent to 2 or 3 mod 4. This is because the integral closure is this here. So I'm not going to have time to do this in class. I did leave this for the lecture notes. But I'll also say that this is a very standard exercise in what's called algebraic number theory. So this is actually not a very hard exercise at all. So this says that if I wanted to compute the integral closure, it's numbers in this form, x plus y wd, where wd is one of these two here. So if d is 2 or 3 mod 4, then O prime is just equal to O, but that's what it means to be a Dedekind domain, that O is integrally closed. So O equals O prime. On the other hand, when D is 1 mod 4, then WD is not an element of O prime, and therefore WD is not an element of O. Right? It is an element of O prime. It is not an element of O. And so O prime is strictly larger than O. So again, if D is 1 mod 4, then the integral closure is strictly larger than O itself. So here's a very down-to-earth concrete example. Say that D is equal to -3. Then this here is 1 mod 4. So this integral domain, z adjoins square root of -3, has integral closure z adjoin zeta 3, where zeta 3 is a primitive cube root of unity. So if I take the zeta 3 and if I cube it, I just get back 1. So actually what this means is that spec O is a singular curve. So yes, this is supposed to look really, really weird because now you have to kind of wrap your head around, well, what does it mean to be singular? Remember that singular says something about the tangent space isn't right. The tangent space really should be one-dimensional, but it turns out that in this case, the tangent space is two-dimensional. So now you have to ask, well, if there's no defining equations, how do you define the tangent space? Remember, you define it using the cotangent space. So here's where we have to look at something like m mod m squared. And you want m mod m squared to be like a one-dimensional thing. But it turns out that when you pick this maximal ideal, twice O, that actually this here has the wrong dimension for the cotangent space. So here, if I were to take a look at p mod p squared, that's not a one-dimensional vector space, it's actually a two-dimensional vector space. So that's why we would say this here is a singular point. Right. So again, this does look weird, but the whole point is that you have to kind of translate everything back into like the Zariski cotangent space and ask what is the dimension of m mod m squared. Right. So I won't really have time to go over this in detail today here in class, but I'm happy to go over this in office hours in case anyone has any questions. All right. So any questions here on these examples for Dedekind domains and integral closure? Okay. All right. So let's try to move on to the new stuff for the day. So what are these quasi-affine varieties? So let's kind of back up with where we are now. So in all of this, I just want to remind you, we are always assuming that F is an algebraically closed field just to kind of keep our life simple. So think of F as like the complex numbers. So of course, affine n space, as what we're used to, should just be a collection of n tuples, right? So nothing fancy here. Now remember that we're embedding affine space into spec by looking at P goes to this maximal ideal. So we're going to abuse notation and think of affine space as spec R, where R is the polynomial ring in n variables. Right? So remember, if you don't like this, you can say, okay, fine, instead of spec, think of M spec, right? Just the maximal ideals. But again, whenever we say affine space, this is actually what we mean. So we're just going to say, think of spectrum of this polynomial ring. Right, so that's affine space. Now I want to remind you, what is an affine variety? So remember, we've been saying that an affine variety is an irreducible, non-empty Zariski closed set. Right, so that's everything in fancy words. So let me remind you more concretely. That is, let's take a look at the following ideal. Right, so again, X here is maybe generated by like M polynomials. So let's take a look at the ideal here. So this is the set of polynomials that vanish at all points in X. So we want this here to be a prime ideal of R. Well, that's equivalent to saying that this coordinate ring is an integral domain. And second, we want this here, the Zariski closure, to be equal to X. right? So again, we want the Zariski closure to be equal to X. So we want this to be Zariski closed. Right, so these are the two that we want. So again, irreducible means that our ideal is prime, which is equivalent to our coordinate ring is an integral domain. And then this fancy phrase, non-empty Zariski closed, just means that X is equal to its own Zariski closure. Right, so this is what we mean by an affine variety. Just like before, we're going to abuse notation, and we'll think of our variety as spec of some integral domain O. So you can also use the fourth or the lattice isomorphism theorem to say, this is just the set of prime ideals that contain this prime ideal IX. Right, so it's equivalent definitions. So notice that if you really want, you could say start with the prime ideal, and then you can define what do you mean by an affine variety. Right, so here's just going to be the set of primes I that contain IX. Right, so this is just a fancy way of saying it. And just to remind you two more things, we'll say that X is non-singular if our integral domain, O, is Noetherian and integrally closed. And finally, we'll say that its dimension is just the dimension of the ring, meaning the Krull dimension of the coordinate. Right, so again, now we have the idea of an affine variety, we know what it means to be non-singular, and we know how to compute its dimension. Right, and the nice thing is that all of this comes from either you start with a coordinate ring O, or you could start with an ideal IX. Right, you can start with either one of those, it doesn't really matter. Okay, so this is what we mean by an affine variety. Okay, so now here's some new things. A quasi-affine variety is a non-empty subset U, which is Zariski open in some affine variety. Okay, so I'll say that again. Let's try to break down what that means. Quasi-affine variety is a non-empty subset that is Zariski open in some other affine variety. Okay, so Zariski open, remember, means this. It looks like it's the complement of some Zariski closed set, and this thing here better contain our ideal IX. Right, so that's just what it means now to be Zariski open. And so this is actually our definition of a quasi-affine variety. Okay. Just like before, we're going to abuse notation. We'll think of this kind of using spec. So either we'll say that U is the set of prime ideals that do not contain this coset, or we'll say that it's going to be the collection of prime ideals that contain IX, but do not contain this subset T. Right, so either one of these will be perfectly fine if you want to use this to define a quasi-affine variety. So remember that if I didn't have this condition here on T, then what's over here is my definition of an affine variety. So kind of putting in this over here is what makes it quasi-affine. So now we can make some definitions just like before. We have a non-singular quasi-affine variety whenever the Zariski closure is a non-singular affine variety. So to compute the Zariski closure, just like before, here I have some set U. I can talk about the ideal of U, right? So just like the zero sets, if you will, because remember that we're kind of dealing with this here. And so now we can talk about the ideal and then look at the zero set of that ideal, and that's what we're calling the Zariski closure. Right, so this here should be a non-singular affine variety if we want U to be a non-singular quasi-affine variety. Similarly, we can define the dimension of our quasi-affine variety as just the dimension of the Zariski closure, right? Because the Zariski closure is itself an affine variety. Okay, so again, for quasi-affine, all we want to say is that it's a non-empty Zariski open subset, and then we just translate everything back to its Zariski closure. If we want to talk about non-singularity or talk about dimension. Okay, so I do want to spend some time going over lots of examples of this, but first, any questions on the definitions here? Okay, all right, let's try to do several examples. Right. Before I go on, let me just remind you that all of these definitions only rely on the integral domain O, a prime ideal IX, and a subset T. So if you give me these three, I can write down all of these definitions here. So you really don't need any equations to writing this down. You just need to know you have an integral domain, that you have a prime, that you have a subset. That's really it. Okay, so first example I want to give is the affine line. Right, so what I mean by the affine line is this here, A1 of F. So it's just going to be elements from our field. Remember, it's algebraically closed. And then we can consider now the polynomial ring, f of x, which we know is a PID, is a principal ideal domain. So that means that every ideal I is generated by one polynomial f. And because we're working over an algebraically closed field, we might as well assume the f factors in this way. All right, so again, we're just going to look at the case when n is equal to 1. So just one variable, in a sense, like one coordinate. All right. Now, on the last homework set, you found that every non-empty Zariski closed subset is in the following form. So either it's the whole line A1, or it's a finite number of points. Right, so that's what every non-empty Zariski closed subset looks like. Either it's the whole thing, or it's just a finite number of points. Actually, since we have the Zariski closed subset, we can talk about its ideal. And we know from the Hilbert-Noeth-Stelsatz that its ideal is just the radical of the ideal I that we started with. Right, so literally if we have a polynomial here, f, that has these weird exponents e1 through en, then g here just says, just get rid of the exponents. Right? That's what the radical does. So I want to point out that this ideal IV is a prime ideal if and only if either g is the zero polynomial or g has one factor. Right, so those are my only two possibilities if I have a prime ideal. So I claim every affine variety is either the whole line A1 or it consists of one point. Right, so that's it. Every affine variety is only in one of these two parts. So here's how you can do this. Well, an affine variety is a non-empty Zariski closed subset. So that means it's at most one of these two here. But remember that it's irreducible. Well, if I have a collection of n points, this is irreducible precisely when it's only one point. Because of course, if I have 2 points in R1 and R2, I can kind of separate them into two different Zariski closed sets. Another way to say that is the ideal generated in this case is a prime ideal if and only if G has exactly one factor. Right, so that's why now we know that every affine variety is only one of these two. So I want to point out that the V's appear at the top. These are Zariski closed subsets, but remember that an affine variety is an irreducible Zariski closed subset. So it's a very specific kind of Zariski closed. So that's why for affine varieties, there are only these two possibilities. So it's a little bit weird that in this case for the affine line, it is very precise. What do we mean by an affine variety? But it's only one of these two. Now, we can think of this in a slightly fancier way by going back to what we said about spec of R. So remember that we can write in a fancy way, A1 is just spec of the polynomial ring. And now let's just stare at the previous theorem. That says that every affine variety is one of two possibilities. Either it's the entire line, this is A1, and that should correspond to this quotient here, where I here is the zero ideal, or it consists of exactly one point. And that one point we can think of as spec F, right? Remember, if you have a field F, spec F consists of exactly one point. And that we can write here as f of x mod I, where I here is the ideal generated by this one polynomial. So this here is a maximal ideal. So this is what's crazy now. Every affine variety X corresponds to one of these two cases, either the zero ideal or a maximal ideal. Well, that's not a coincidence, because notice that spec of our ring, what we're calling the affine line, consists of one of these two ideals. Either inside a spec of R, we have the zero ideal, or we have a maximal ideal. And remember that we proved the theorem that the maximal ideals are all in the form x minus r, where r is in the field F. So we actually have the following result. All affine varieties X, even using this fancy language, are in the form spec of R mod I, as we range over the ideals in spec of R. So this is what's crazy now. All of the affine varieties all correspond to the prime ideals in spec of R. Right, so this is what's happening. Everything corresponds to spec of R. Right. I want to point out that this also relates to something we saw earlier. If you really are wondering what's going on here, well, me saying that X is a subset of the affine line is the same thing as saying that there is an embedding from X into A1 of F. Well, there's a way you can think of this embedding. It's actually coming from the pullback map on prime ideals, which actually corresponds to this ring homomorphism that says take R going to R mod I. So again, that ring homomorphism, R going to R mod I, corresponds exactly to this embedding X going into spec of R. Right, so all of this does match up with everything that we've been doing up to this point. Right, so again, all of my affine varieties correspond to ideals I in spec of R. Right. Okay, so if you give me a minute, let me maybe try to say a little bit behind what's happening with the quasi-affine. So just to put this up here to remind you, every affine variety X is one of two possibilities. Either it's the whole line or it's just a point. Right, so one of these two. Now, we can use this to compute what the quasi-affine varieties are. Remember that they have to be non-empty, and they have to be complements of Zariski closed sets. Well, we know what every Zariski closed set looks like. Right, so essentially they're going to look like a finite number of points. So if you just kind of piece all of this together, either you'll have exactly 1 point. So this will be what happens if X is 1 point. But then in this case, Z of t only has one or two possibilities. Either Z of t is 1 point or Z of t is the empty set. If Z of t is 1 point, then you here would have to be the empty set, which can't happen by definition. On the other hand, if X is the affine line, Z of t here can't be all of the affine line, because then again, I'd have the empty set for U. So Z of t has to be finitely many points. Z of t could itself be the empty set, but Z of t here has the most finitely many points. And so then that gives the second possibility here. So just to kind of recap, what we've actually shown now is the following. Every quasi-affine variety U is either 1 point, or it's the affine line minus a finite collection of points. Right, so that's what every quasi-variety looks like. So notice that this almost looks like what we had up here for affine varieties. So we know that every quasi-affine could maybe consist of 1 point. Well, if it consists of 1 point, that quasi-affine is actually an affine, or it can maybe be the affine line minus a finite number of points. Well, that's kind of the generalization of just being the affine line itself. But look, in both cases, if I were to look at the Zariski closure, in the first case, then I just get back that affine variety of 1 point. And in the second case, I get back the affine line. So what's happening here is that in both cases, the Zariski closure is an affine variety. Right. All right, so this is what's happening now when we're dealing with the affine line. So we know exactly what affine varieties look like, we know what quasi-affine varieties look like, and we even know something about the Zariski closure of these things. Okay. All right, any questions on any of this today? Okay, all right, great. So next time then, I'll say a little bit more about one last example, what are called hypersurfaces, and then I want to go over the definitions of a quasi-projective variety. And then this will kind of wrap up everything that we've talked about so far with varieties. From there, I do want to finish off the course by going over what's called the Riemann-Roch theorem. And roughly speaking, what I want to answer really two more questions. Number one, what do we mean by a projective variety? So how do we really define an elliptic curve in a more general sense? And then number two, how do we prove the group law for an elliptic curve using some of this fancy language? And we're actually going to prove the group law by using this thing called the Riemann-Roch theorem. Okay. All right, well, thanks for your time and attention then. Let's go ahead and call it a day. So I'll be around for office hours if you have questions later.
Thanks very much, Professor.
Thank you.
Okay. All right, you're welcome. Okay, take care. See you then.
Professor.
Yeah.
I just wanted to ask yeah, today I don't think I'm gonna be able to make it to the 101 lecture.
Okay.
I have like a scheduled appointment with my clarinet teacher.